Okay, so next example, we have the limit as x is approaching negative infinity. We have the cubed root of x minus the fifth root of x. That quantity is all over the quantity, the cubed root of x plus the fifth root of x. First of all, we need to make sure we have radicals here and that when x is going to negative infinity, this is part of our domain. It is okay. And because these indexes here are odd, I can take an odd root of a negative number and get back a real number. And so I'm okay. If one of these were the square root of like x, then it would not be okay. I can't go to negative infinity, take the square root of a negative number. Oops. Okay, so that's okay. But now when I go in here and I go in and I plug in negative infinity, where I see an x in this, it really doesn't tell me anything. I'm not really sure what that means when I have this infinity minus infinity. Actually, let's think about this. If I take a cubed root of a negative number that's getting really, really small, then the cubed root of that negative number, that's still going to be going to negative infinity. It would be come back a negative number. Minus, if I took the fifth root of a negative number going to infinity, that's still negative. So this would be minus infinity. All over. So same idea. This would be negative infinity plus a negative infinity. Okay, but I really don't know what negative infinity plus infinity is. I don't know if one function is growing faster than the other or not. And negative infinity minus infinity. And so this really doesn't tell me much. And this is the indeterminate form. And so we want to go back and manipulate it to see if we can get back some number when we take the limit, or if it shows us that it's going off to infinity or negative infinity. I can't spell. Okay, so we want to, let's rewrite this. And let's, instead of writing radicals, let's rewrite that. Radicals can be rewritten with rational exponents. And so recall, if you had the nth root of x, this could be rewritten as x all raised to the 1 over n power. So I'm just going to rewrite this without radicals. And so let's look at the numerator. And so this cubed root of x, this is the same thing as x raised to the 1/3 power minus the fifth root of x. So this is x raised to the 1/5 power all over the cubed root of x, so x to the 1/3 plus x to the 1/5. So again, plugging in negative infinity, this still is giving me back the same thing. But let's use that trick that we were talking about before. Let's divide each term by the highest degree of the variable in the exponent. By the variable raised to the highest power that's down in the denominator. So in our case, we have to determine is 1/3 a bigger number or 1/5 a bigger number? Well, 1/3 is 0.33333, 1/5, that's 0.2, 1/3 is the bigger. So I want to divide everything through by 1/3, x to the 1/3 power. So we can multiply this. Another way to think of that is by a fancy one. 1 over x to the 1/3. 1 over x to the 1/3. And so again, we're using some rules of exponents because when we divide, so we have the same base, b to the m over b to the n. And let's say n was a bigger number. Then we rewrite this as 1 over b, take the exponent on the bottom minus the 1 on the top. So when we distribute, bring down a limit, we haven't taken it yet, as x is approaching negative infinity. So this is x to the 1/3 all over x to the 1/3 minus x to the 1/5 all over x to the 1/3, x to the 1/3 all over x to the 1/3 plus x to the 1/5 all over x to the 1/3. So 1/3 is the bigger number, exponent. And so for each fraction in there, we're going to rewrite it. So notice x to the 1/3 divided by x to the 1/3, that's just 1, minus 1 over, maybe we can do the work here, down here. So we're going to have 1/3, the exponent on the bottom, minus the exponent on the top, 1/5. We need common denominator in order to add fractions or subtract fractions. So our common denominator 3 and 5 is 15. So doing that, we get, this is 5/15 minus 3/15, which is 2/15. Okay, so this would be minus 1 over x to the 2/15 power. All over, so again, x to the 1/3 all over x to the 1/3, that's just 1, plus, well, we just did that work. 1/3 minus 1/5, so this would be 1 over x to the 2/15. Okay, so now when we're going to negative infinity, and we have 1 over something that's going to negative infinity, that value is going to be approaching 0. And so when we go in and we plug in negative infinity, wherever we see an x, and since that's x is in the denominator and there's no x in the numerator, this goes to 0, and this one goes to 0. So now when we look at that limit, this is going to give me 1 over 1, which is 1. So as x is approaching negative infinity, if we looked at that graph, the graph would be getting closer and closer to the y value of 1. So we had talked about asymptotes. Let's look at one of those. It is actually, before we do that, it is possible to get one of these examples where you're not getting a number. I don't know if you want to see one of those. Actually, let's just do it real quick. For instance, if you had had the limit as x is approaching negative infinity of 1 minus x cubed all over x squared plus 7x. And this is raised to the 5th power. So if we go in here, we plug in negative infinity wherever we saw an x. Well, that would technically give me 1 minus negative infinity cubed. Well, if I take a negative number and I multiply it by itself in negative or odd number of times, that's negative. And then I would have this minus in front. So it'd be like 1 plus infinity. So I would see that my numerator was growing towards positive infinity. And then if I look at my denominator, so remember when we were looking at polynomials yesterday, we talked about looking at the variable raised to the highest power. And that was really what determined what happened to our end behavior of the graph. And so if I look at just the x squared and I squared the negative, that's positive infinity. So we get something like a positive infinity over positive infinity raised to the 5th power. But again, that doesn't tell us anything. And so we need to go back and we need to manipulate. So we could use our rules of limits if we wanted, and we could say, we're taking the limit of this rational expression, and then we're going to raise it to the 5th power. So now, and raise it to the 5th power out here. Again, infinity over infinity. But if we use what we were just doing, that trick, look at the variable raised to the highest power in the denominator. And when you do so, notice that it's an x squared. So we're going to multiply every term by 1 over x squared. And so we have the limit as x is going to negative infinity. And we distribute this 1 times 1 over x squared is 1 over x squared minus x cubed over x squared. Well, the power is higher in the numerator, so that's just a single x left, all over. So 1 over x squared times x squared, that's just 1. And then we have 7x over x squared. So that would leave us with plus 7 over an x. So now when we look at this and we plug in infinity wherever, or negative infinity, wherever we see an x, notice this 1 over negative infinity quantity squared, that goes to 0. If I plug it in negative infinity into this minus x, well, that's minus a negative infinity. To me, that piece right here tells me it's going to infinity. And then I have the bottom. Well, x goes to negative infinity of 1. It's just 1 plus the 7 over negative infinity. This goes to 0. So plugging in infinity and kind of getting the reasoning, we have this infinity over 1. So technically the limit doesn't exist, but it's telling me if I graph this, my end behavior as x goes to negative infinity is going to be shooting upwards. So if we graph that function, we know that it's shooting upwards as x goes to negative infinity.